welcome to this presentation where we go through Unit 2 of WJEC Physics, where we look at how we generate electricity. Okay, so our objectives for this presentation are as follows. We're going to understand the key steps in a fossil fuel power station. We want to evaluate the different energy resources, calculate the efficiency of energy transfers, and then describe and explain how the national grid increases the reliability, efficiency and safety of power transmission. Okay, so here we have our useful links for this section, a whole variety of videos detailing the different types of power stations and energy resources available, along with a couple about the national grid as well. Don't forget, although it's not here, Seneca, the link to the appropriate Seneca is in the Unit 1 presentation. Okay, so on to our first type of power station, and arguably this is the most important to the UK, as it's these power stations that generate the vast majority of our electricity, hence why we hone in on this type in more detail than the rest. So key things for you here: you've got to learn the key stages and the energy transfers that take place. Okay, so we start off with the furnace. And in the furnace, here, we are going to take our fuel and we're going to burn it. Burning it, we're going to release the heat energy, which we're going to put into water, making it steam in the boiler. That steam goes into a turbine, which is basically a giant fan, which the steam pushes round and round and round and round and round, converting the heat energy from the steam into kinetic energy in a shaft. And then with kinetic energy goes to the generator then creates electricity from that motion, electrical energy. If you want to see this in more detail, there's a link to a video I did about power stations in a lot more detail on the useful links. If you're watching this on YouTube, there will be the card that appears above me. The main advantage of fossil fuel power stations there is that they are very reliable. We know how much energy we're going to get out based on the amount of fuel we put in. And for a small amount of fuel we get quite a lot of energy out. The main disadvantage though of fossil fuel power stations is that they are non-renewable and they all release carbon dioxide. I'm going to lump in here nuclear power stations, because nuclear power stations work in a very similar way. If it's a nuclear power station, we replace the furnace here with a reactor instead, using uranium as the fuel. Obviously their main disadvantage is the radioactive waste that they produce. Okay, what about renewable power stations then? So we're going to lump pretty much all the different renewables in together here. Now renewable, what we mean is that it's quickly replaced by the environment. We can't use that resource again. You know, once wind has gone past a wind turbine, we can't reuse that wind, but it's quickly replaced by the environment. The main advantage is because they're renewable, they don't run out. Not in the short term anyway. You know, we're talking billions of years. You know, when the Earth disappears, then obviously they won't be around. But in the short, or in our lifetimes, no, they're not going to run out. The main disadvantage is they're unreliable. So if you think about solar panels, they won't work at night. They don't produce electricity when it's dark. And on a dull day they won't produce as much electricity as on a sunny day. Wind turbines, if there is too much or too little wind, then they don't generate any electricity. If the wind's too strong, they have to shut them down, otherwise they set on fire. If you want to see that, there is a video of one from Scotland, I think it is, that is on the BBC website, that it set on fire basically because they couldn't turn it off quick enough. The other problem with them is they do need an awful lot of space to generate enough power. To generate similar amounts to power stations, you're talking thousands of wind turbines. So this link here, I'll put it in the description for those of you watching this on YouTube, goes into a deep dive of the advantages and disadvantages of each type of power station that I'm not going to do here. Okay, so efficiency. Any energy transfer will not be 100% efficient. By this we mean that some of the energy will be wasted. Now the two normal ways energy is wasted are as heat and as sound. But it could possibly be light as well. in certain situations could be like, but generally heat and sound. If you've got to guess, heat and sound, or heat or sound, will be the wasted energy. Generally caused by friction between bearings and things like this, surfaces moving past each other. That's where we're going to lose our energy. Now, efficiency is where we're talking about what fraction of the energy is usefully transferred. In most questions, they're not going to tell you what the useful energy transfer is. They're going to expect you to be able to reason that based on the information you've been given. Here is an equation then for it. So efficiency is going to be useful energy divided by total energy. Now, we covered back in Unit 1, we talked about the difference between energy and power. Power being the rate of energy transfer. So in fact, you don't always have to use energy to work out efficiency. You can also use power as well. And yeah, classic mistake you see with students here, they do the sum and they put a number in somewhere and they get a number over 100%. So bear that in mind. You cannot have over 100% efficiency. If it's a real world situation, it probably would be below 50%. Okay, so a really useful way of showing efficiencies is with what's called a Sinkey diagram. Now, Sinkey diagrams, they show it pictorially. We as humans are very, very good at picking out patterns, picking out information based off a picture, where we might struggle to get it from a table or just from a pile of numbers. So this is where the Sinkey diagram comes in. Now, the input energy is always on the left, and it always goes from left to right. And the useful energy will be coming out on the right, and the wasted generally will go down. Occasionally you'll see it go up, most of the time it will go down. Now, in a Sinkey diagram, the width of the arrow, like this, the width of this arrow is the important part, okay? So the width of that arrow tells us how much energy or how much power is in each section. Take care, if it's got an arrowhead, it is not the arrowhead that matters, but it's that shaft going to the arrowhead. So always remember, it's not the width of the head, but the width of the shaft that matters. Okay, so the national grid. National grid transmits power from the power stations to consumers. And in there we use things called transformers to change the voltage for efficiency and safety. Okay, so our national grid increases reliability. Now, we in the UK don't just rely on one source of power, we use a mix of power. It's important that we use a mix of power because it does things like reduce our CO2 emissions. It means that we can get the cheapest supply of electricity possible as well. So when one source is particularly expensive, we might not use that one so much. We might go to something different. But also, one of the things that the national grid does very well is if we end up with a power station going offline. So for example, wind turbines, got to go offline because it's too windy. Or you've got to take a coal-fired power station offline because you've got to do some repair to a boiler. Or you've got a problem with a nuclear reactor where you need to switch it off. Obviously, if you just had a power station supply in a town and you had to switch that town's power supply off, the whole town wouldn't have any electricity. So by using the national grid, we can very quickly switch from different power sources as they become cheaper, more expensive, as demand goes up, as supply goes down, etc, etc, etc. The other thing we can do is if we've got a shortage of power produced in the UK, we can import it. So we've got links to places like Ireland, to Spain, I think off the top of my head, to France, definitely to France, and to the Netherlands. So what we can do is they might have an excess power, we might not have enough, we'll buy it off them, and vice versa. So there'll be times when, for example, it's quite windy, our wind turbines are going really well, and maybe Spain's solar panels are not going so well, it might be a bit cloudy down there. We can pass our electricity on to Spain because we can't store anything. Now when it comes to efficiency, our national grid increases efficiency. So whenever you pass electricity through a wire, you have resistance, and that will heat up the wire. Now if you're dealing with this sort of electricity where we're dealing with thousands of volts, you're going to end up, and thousands of amps, you're going to end up heating up wires quite quickly. So what we need to do is keep the current as low as possible, because it's the current, the rate of flow of charge, that is actually going to cause the heating. That charge can have a really high voltage and no problems as long as the current is low. So to increase efficiency, we try to make sure the transmission voltage is as high as possible. So what we have is what we call a step-up transformer. Steps the electricity up to go through the transmission lines. This lowers the current, lowers the heat loss in the wires, makes it more efficient. And then our final way our national grid helps is with safety. Now, transmission lines are going to be in the thousands of volts. If you were given electricity in your house in the thousands of volts, the minute you put your plug anywhere near the socket, you'd get sparks, and that's not very safe. So we drop it to a safer level. Now, mains voltage, still not safe, still going to cause you a lot of harm if you end up going through your body, but it's a lot safer, and obviously, so that's where we do. So we have a step down transformer that steps the voltage back down to safer levels for consumers. Okay, so here we have a diagram of the national grid. Now, it's important that you learn the pattern of the voltages, not the actual numbers. So you need to know that whatever is generated, the first transformer will always be a step-up transformer. Remember, we step up the voltage to make it more efficient. Then any transformer after that will be a step-down transformer. So we would have a step up, then a step down, then we should have another step down here and another step down here going to our homes. So in this case, our power station probably is going to supply the electricity at something like 25,000 volts. It's then going to step up to one of these voltages. I think in the UK, this isn't a UK diagram it looks like, but in the UK our super grid runs at about 500,000 volts. Then we step down to different consumers depending on their usage. So for example, the heavy industry might get 11,000 volts because they need the extra power that gives them. You might find that factories, and I think the school probably, gets a 400 volt supply because some of the things like the kitchen equipment, perhaps if we've got big lathes, in DT, some of the bigger saws perhaps need a lot of power to get them going, so they get a higher supply. Then obviously finally step down to domestic use, so your house will get 230 volts, which will be your domestic supply. Okay, so over to you. Either if you're watching this on YouTube, click the link in the description to get these questions, or if you're watching this as a PowerPoint, stop the presentation. If you click on that document, the question paper should open up, give you a chance to answer some questions based on this topic. When you've had a go at them, if you go to the next slide, that has me doing a review of these questions. Okay, so welcome to this video. Now going through this set of questions on generating electricity. So same as before, hopefully if you've looked at number 1 on electrical circuits, what we're going to do is the idea that you've gone through these questions first yourself, or you could be doing them as I'm going through them, having downloaded them off the previous slide. Okay, so this first question. Diagram below shows the main parts of a thermal power station that uses coal to produce electricity. You've got to complete the labelling, so you're going to write in that box there. Bit that's missing, the furnace, we've got steam, something connected to the generator, so that's the turbine. Then you're drawing one line from each part of the power station to the energy change it produces. So the furnace is where we are going to burn our fuel, and we are going to take the chemical energy in the fuel, it's going to become thermal energy. And then our generator takes kinetic energy, movement, to become electrical energy. So you should have two lines going in an X pattern like so. Okay, so some values for this power station are listed below. Use this information and the equation below to calculate the percentage efficiency. So what we're going to do here is we work out percentage efficiency. So our percentage is going to be, let's just make my percentage sign a bit bigger, is going to be the energy usefully transferred. So it's a power station. The useful energy here is going to be our 4,500. And the total energy supplied is the input energy. So that's 15,000 times by 100 to give us a percentage. And that is going to be okay, so it's going to be our number we've got there, so 4,500 divided by 15,000 times 100. It's going to be 30% efficient. Okay, so combined heat and power station. So let's look at this question. This is the higher tier version of the question we've just looked at. Describe how electricity is produced by a fossil fuel power station. 3 marks. We're looking for 3 stages. We're only looking for describe, no explain. We're looking for quite simple stuff here. So we're going to have our fuel is burnt to heat water to steam. The steam turns a turbine. Steam turns turbine. Turbine turns generator, making electricity. Alright, simple as that. Alright, then the second bit of this question then. So, Sankey diagram shows the energy transfers for a combined heat and power station. 75% of the input energy to the power station is transferred as useful energy, some to the national grid, some to local heating. 40% of the useful energy produced by the power station is transferred to the national grid. Okay, so this question, let's just bring up a new page of stuff. That way we can keep going. So this question is quite tricky. It involves a double percentage. So 75% of the input power is transferred as useful energy, and then of that 75%, 40% is transferred to the national grid. So it's not 40% of the total energy goes to the national grid. It's 40% of the 75%. So Helen thinks that we have 20 megawatts of power going in. So let's have a think about this. So 3.2 equals 40% of our 75%. Okay, so what we can do is we know that 32 times by 100 divided by 40 is going to be our total useful energy. So we do that on the calculator. 3.2 times 100 divided by 40 is 8 megawatt hours. So the total useful energy is 8 megawatt hours. Okay, so now we need to know what the total is. Well, 8 is only 75% of the total energy. So 8 times by 100 divided by 75 equals 8. Is 10.67 megawatt hours. So Helen is incorrect. And like I said, most people, when they got this wrong or struggle with this question, is because of that double percentage. Okay, so over the page, the final bit of this question: another power station produces 1200 megawatts at a voltage of 50 kilovolts. The voltage is increased to 400 kilovolts by a step up. Use an equation from page 2 to calculate the current in the wires of the grid. Assume that the transformer is 100% efficient. Okay, so let's get a new page here. Okay, so we've got an initial power of 1200 megawatts. It's 100% efficient, so we've got a final power of 1200 megawatts. We've then got a voltage of 4000 volts. We want to know the current. So current is going to be power divided by voltage. So it's going to be 1200 times 10 to the 6, counting for the mega, divided by 400 times 10 to the 3, accounting for the kilo. So that gives us a total current of 3000 amps. Okay, so on to our first, just remove them, don't need them now. Okay, on to our first of our QER question, our QER question in this topic. Domestic electricity is supplied by the national grid, is generated in the UK in a variety of power stations. Describe how the national grid is used to supply electricity to consumers in a reliable, efficient and safe way. So, already been through this question when I looked at QERs as a homework for Year 9 and Year 10. Got some stuff on that. If you've already seen it, brilliant. That will help you with what we're doing now. So, we'll start off. What I'm going to do is, rather than do this in prose, I'm just going to do it in note form. If you're doing this question properly, you should try and write it in continuous prose. But by doing it in note form, I can get the important stuff down a lot quicker. I might lose 1 mark for the way I've written it, but that I will get all the information. So I'm going to start off with reliable. So how does it make our thing reliable? Well, we can quickly replace power stations that go offline. So for example, if it's too windy and we have to take wind turbines off, we can do something about it. If for example we get a coal-fired power station that suddenly stops working, we can do something about it. So that's how they make it reliable. You can change where you're getting your electricity from so that you can take into account fluctuations in supply. Now in terms of efficiency, we step up the voltage to reduce current, and in doing so we reduce heat lost in wires. Then our safety, how do we make it safe? Well, we step down the voltage to safer levels for users. And that's basically what you need for your 6 marks there. Like I said, written that way, probably get 5 because it's a bit scruffy, but it's got all the key information down. Okay, next part of this question. The chart below shows the number of units of electricity used each day per person. Alright, so we've got a graph. Name one country in which people use 3 times as much energy as in Germany. So Germany used 4.3. We're looking for one which is 3 times as much as that. So we've got a choice of Sweden or Norway. Norway is closer to France. It's closer than France. Sorry, let's start that again. Norway is closer than France to Earth's North Pole. Explain how these countries may account for different amounts of electricity consumed in these countries. So Norway is going to be a lot further north, so it's going to be colder, and you're going to need your lights on for longer. Those are your 2 marks. So because it's further north, you're going to need more electricity for heating. It also will have longer nights, so you'll need more electricity for domestic lighting. The cost of a unit of electricity is around half a UK cost, and suggests that a person's electricity bill in Norway could be half of that paid in the UK. Use the information in the chart to explain whether or not you agree with this. Whether you agree with this suggestion. Okay, so they use half as much. Sorry, the unit is half as much, but they use 4 times as much electricity. So if you think about it, the bills in Norway are still going to be twice that of the UK. Yeah, so if we just make a note of this one, so the cost per unit is half, but they use 4 times as much. So if you did 4 times a half is 2, so the bill in Norway is 2 times the UK. And it's always good practice in these sort of questions to put that you disagree. Okay, and on to the final part of this question then. Calculate, in 2002, the average UK family consisted of 3 people. Calculate the number of units used by this family in 1 week. So we go back up to the graph. That's 5 daily units per person. So we're going to have 3 times 5. So 3 times 5 for the population, times by 7 to make it a week. So that is going to be 3 times 5 times 7, 105. Key thing there is to remember the graph is for 1 person and there are 3 in the average family. Use an equation from page 2 to calculate how much this family would pay for electricity in 1 week. Cost of electricity is 8 pence, so we're just going to do 105 times by 8, which is going to be 840. They want it in pence, so we'll leave it like that. Okay, now this question was a brilliant one when it was put on the exam. Really stretched, and students really struggled with it. I think a few things. 1, the graph's got an awful lot of information on it. 2, people confusing their different power sources. And 3, just some horrible parts to the question. So, got a whole bunch of information. Use the information from the diagram to describe the trends in the use of the individual fossil fuels and the total fossil fuel is shown over time. Okay, so we look at this graph and you can see, first things first, black on the bottom, so that's coal. We can see that coal is declining. So overall, coal declines. Okay. Then we look at the next one, the next fossil fuel, which is gas. And if you actually look at this, gas probably stays roughly the same. So gas, roughly the same, because if you look at this line here, they're all about the same length. And then our third fossil fuel is oil. Goes right on the very top, and again oil is roughly the same as well. Then our final part to this, the overall. Well, if these two are roughly the same, coal is declining, overall is declining. Alright, the use of nuclear power for production of electricity remain roughly constant. Suggest possible reasons for this. Okay, well, we're looking for two possible reasons. One, there's been no new nuclear power stations. And secondly, no nuclear power stations, or no nuclear has been decommissioned. Yeah, so not put any new ones on, we're not taking any old ones off. Production of electricity from renewable energy sources remained roughly constant. However, there was a reduction in the contribution of wind and a change in the contribution to solar. Describe how weather conditions were different. Well, if we've had less wind, we're looking Q2 2015. Oh, we can't see on that graph anyway. So if we've got any difference, it probably means that it was sunnier. So the overall contribution of renewables was roughly the same in those two. Yeah, roughly the same. So therefore, if wind has gone down, it must have been sunnier and not as windy. Okay. Next question then. Bring up a new question. Alright, so the first four carbon budgets. So this is all about carbon now. Calculate the targeted percentage drop in CO2 from all sources between 1990 and the end of 2022. Show your workings clearly. Okay, so oh, there we are. Right, okay. So we started off, we're looking at percentage drop. That's going to be our actual drop divided by our original value times by 100. So our actual drop is we started with 39,000 million tonnes, and by the end of 2022 we were down to we want to be down to 2,544 million tonnes. So the actual drop we need is the difference between those two numbers, times it by 100, and that gives us an actual drop of 34.8%. Rounded up, because I've got a number that's reoccurring, so I'm just going to leave it to one decimal place. That's enough here. Alright, so between 1990 and the end of 2022, the mean percentage drop in the use of fossil fuels in the production of electricity is expected to be 40%. Comment on the progress being made in achieving the government's overall target. Well, that's great. Alright, so we've got a good start. But no information about other CO2 sources. So it's brilliant. We know how we're getting on with fossil fuels, but what about everything else? What about factories? What about cars? None of that is in there. Okay, thanks for watching this review of the questions. Any other things, put them, send us comments, that sort of stuff. Okay, thanks for watching this video. Well done for making it through right the way to the end as well. If you liked it, click like. If you got any comments about stuff that's missing, any improvements, anything you didn't understand, leave them in the comments below. If you look around me, there should now be the playlist for all of these videos, along with YouTube's algorithm recommended one of our other videos that you should go and watch. Also, don't forget to subscribe to the channel, follow us on Twitter, link in the description, just to see the other sort of stuff that we produce.